How's it going, everyone? Welcome, Ulier Gonzalez here, and today let's going to talk about is the second book of You Don't Know series, the You Don't Know JavaScript Yet series, second editions of the scope, right? So we can dive deep into this particular topic and to have a deeply sense and a deeply understanding of what a scope is, especially in English, because my main language is not Spanish. So I, up to certainly point, I quite know what is this, but I don't know how to describe this in English. And also, it will gonna help me in my thinking process to understand well how the machines actually uh, understand for what a machine understand for a process and for a scope. So let's get into this. So by the time you have written your first few programs, you're likely getting somewhat comfortable with creating variables and storing variables in them. So working with variables is one of the most fundamental things we do in programming. But you may do not have considered very closely the underlying mechanism, which is one of the reasons why I'm doing this, is to understand that mechanism used by the engines to organize and manage these variables. I don't mean how the memory is allocated on the computer, but rather how JavaScript know which variables are accessible by any given statement. And how does it handle two variables on the same name? Okay. So how does it handles two variables of the same name, which is something okay. Depending of the mode, you can handle that. But in any case, uh, how does JavaScript know which variables are accessible by any given statement? And how does handle the two variables of the same name? The answer to the questions like this, take the form of a well-defined rule called scope. So the variables or how JavaScript how does JavaScript know which variables are accessible by giving a statement? Okay, giving it a statement, how JavaScript know which variables are accessible at that moment. And the other is that how it handles if two variables of the same name. You can have variable of the same name. All right. But what it's gonna do is to override that. Exactly. So what it's gonna do is to override in the case of var, but in the case of let, it will do that the same. You know, you just want to override that. Of course, you're gonna throw an error because you can redeclare that. And not even counts because you can reassign them. But var does work in that way. So this book will dig through all the aspect of a scope, how it works and what it's useful for. Gotcha to avoid and then point toward common scope patterns that guide the structure of programs. Or first, okay. So the answer to these questions, like this, take the forms of a well-defined rules called scope. This book will dig through all of this aspect, how it works, why it is useful, so what is useful, gotchas to avoid, and then point toward common scope patterns that can guide the structure. So the mechanism, why it is useful, something to avoid, some gotchas to avoid, and the pattern that unlock, which is the model, or how to structure your programs. So our first step is to uncover how JavaScript, the engine, process our programs before it runs. Let's get into this. So welcome to book 2 in the You Don't Know GS Jet series. If you're already getting started, if you're already finished, get started, the first book, you're in the right spot. Yes, I already did that. Just to make a quick overview of that particular book, first we talk about is what is JavaScript, who makes that, who owns the legal trademark, the people who oversees the technical spec called TC39, why it is what is why it is role, who made these people, where they come from, and what is their motto, which is don't break the web, and what is this committed. So what is the role of this commit, right? Is to now propose or improve the language by proposing champions or proposals. They need to wake up to 5 stage, from 0 to 4, to make all the way up to the spec, right? Now, I also look at the that despite that the DC39 is using its best efforts to guide the ECMAScript, the reality of the web is quite different. And because of this diversion here, well, sometimes they have to go back to redraw some of this spec. And that is a particular case interesting, that's not relevant for today's video, known as Smushgate, right? And how now, because they want to guarantee that the web don't break, we can use things like polyfills, which are features that allow us to use the latest syntax and providing backward compatibility to all the browsers, and recognize that JavaScript, this console that comes in the browser, is something that is not a true spec compliant ECMAScript. Also, the diversity of runtimes that we can run JavaScript, whether it's on the client, the server, libels, and robots, the only reality that matters from the spec perspective is the web, right? We also talk about is the different programming paradigms, so Java's functional, procedure, object-oriented programming, as well as how the JavaScript engines work, briefly speaking. All right, what is the compile? What is an interpreter? Why JavaScript is a compile language? Because the way how it handles errors. And since this is now a parsing phase or a compile phase, a lot of the time people in the community thought that JavaScript was not fast enough, and they make some attempts to show that, well, it can, such as the ASM.js, which is now a subset of JavaScript that now provides some hints to the JavaScript engines that Mozilla developers back in 2011 and 2013 they were able to port now as a game from Unreal Engine into the web. And because this set a precedence that JavaScript fast enough, years later, or years by, or after years by, it turns out that the spiritual successor known WebAssembly now take this idea and push that a little further by saying, hey, instead of worry about the parsing phase, that's going to skip that parsing phase, create this intermediate representation of a language that looked like an assembly that allow us is to not only pour Unreal game engines, all right, but also is to pour any program written in any programming language, and then compile that into WebAssembly that can be run in this web environment. This is why WebAssembly has become now a portable, a universal portable target, a universal compiler target. So since the language is now still concerns about that the language is not fast enough, well, the idea is that with this strict mode, this is something that has from over more than a decade, from EX5, we have now some guidelines that we as developers must follow in order to provide in order to provide good in order to provide our code and have good chance for the JavaScript engine to optimizing and running our code. So this is just the chapter 1, okay? To understand briefly about what is JavaScript, and then on the chapter 2 is the serving JavaScript. We look about what is a program, how JavaScript sees programs, what values are, why we have different types of values, what they represent. We have now primitive and objects, and also arrays and functions, and why functions are quite powerful here. Also, how we can define is our values, whether it's as a literal or held inside of a container, as a variable, which is something that we're gonna see that, and how important is this creation of these values and understanding what is going on, because it's going to set now a precedent for this particular chapter, this code. So what are the different syntax forms that we can go with, such as var, lets, and const, and also how you can define is variables using a functions definition. Also inside of the function parameter body, or the parameters in a functions where you can have access in the side of the body, and the different roles of a function here, such as whether it's a procedure or the strict mathematical sense of a functions. And because of that, that we can define different ways of function, whether it's a function expression, whether it's and a function's declaration, what actually means that. Also the comparison and the equality, how now JavaScript compared to compare values, okay, whether it's they are different or if they are the same type, okay. So with that, we also look at that because the way how it compares from JavaScript perspective is based on this referential identity. So also how now JavaScript converts value from one to another using abstract operations, okay, and then how we can now organize our code, whether it's using is a class syntax, this object-oriented programming, which is a syntactic sugar, and the how do you call it? And the functions and models, right? This is just serving JavaScript, right? That particularly chapter. And in chapter 3, we get into the roots of JavaScript that affect every virtual line of code that we write, so we can understand now the ebbs and flows of the feel of JavaScript, which first is the iteration. What is an iteration? Which is a design pattern, all right? that most of the time it is useful because when we write a program is because we want us to now uh, consume data and process them so we can make decisions on that most of the time, right? So there's a particular standard of how we can now consume these uh, collections of data one chunk at a time, right? And then it used now a particular protocol called the iterator, okay, that describe now a contract or an object, okay, that has a reference to the underlying data structure, and we can now have access uh, to the collection by calling the function that the iterator exposed. So when we call the next function, we can get that value as well as the boolean value that say, hey, we are done. And this is now how we can is look at this particular way or algorithms to consume data one chunk at a time. So the way to consume that is by using is whether it's a spread operator or the triple operator here, the spread operator, or the for of, that both of the syntax is going to look at that particular expressions, whether it's a conditional expressions or a conditional expression, a functions, async functions, generator or async generators that produce a value. If that value that it produces now has in its inner properties the reference to the reference to this well-known symbol known symbol.iterator, which is like a badge that say, hey, this object now implement the iterator protocol. It knows how to consume this kind of collections and then expose that one chunk at a time. So instead of doing that manually, those syntax forms actually now automate that process for us. We're going to continue to call that until there is no more elements. So we also look at these iterators that now needs to look up to an iterable, where is the data structure that is now a sequence, okay, whether it's a map, key, set, whether it's a map, set, arrays, or a string, and also is the concept of or the properties of functions such as scope and closure, all right, which is the way of remembering variables that are outside of its inner scope that it continue to use in the inner scope even after this function is executing in a different scope. Okay, so this is closure. And this is useful how we look at the different forms and how can we create closures, okay? And also is the this, which is another property of the functions that allow you to now have access to a particularly global object called execution environments, where you can now is dynamically pass attributes. And because this dynamic nature that allows us to access properties, it matters how the function is called, right? So because another property is the prototype, which is a property from objects, okay? Prototype is now this mechanism of how now a particular object resolve the property access between a series of objects that collaborate with each other. So if the object B that that are from object A, and it tries to have access to a property that doesn't know, it's going to now delegate that to the object A to to the object A to look up for that property. And this series of links that create among different objects, now it is known as the object. It is known as the prototype link or the prototype change, right? So we look at how to do that, what is that, and when it comes to combine this with the object of prototype, okay, we look that this is the way of how we can now extend our programs by adding now properties dynamically to this context, okay, and as we now pass, so this is a way with the prototype linking into this is a way of how can we now is extend the functionality of our program through delegation. So in other words, you can have now the data there, all right, and anytime you define is a functionality, all right, you're going to now pass that data to that particular functionality that can be now that can be different of that shape, but as long as have that property, it'll be what it's supposed to. So this is when things started to get interesting. This is the reason why I'm actually looking at this particular book, the chapter 1 and what the scope, okay, where here is describing is how important is for us to understand is that variable is one of the most important topic in any programming language that allows to write our programs. And here we're going to focus not on how that is allocated, okay? We're going to see how is JavaScript knows at which variables to use at that particular statement, and how now it knows or how to handle is when two variable has the same name. All right, variables resolutions here. So the answer to this question is like this. So let's get into this, right? About this book. So that was just to summarize the first book. Okay, that was quite mind-blowing. 20 minutes I used to do that, and you're in the right spot. If not, before you proceed, I encourage you to start there for the best foundation. So our focus will be the first of the 3 pillars in JavaScript, which is the scope, the object, the scope, the objects, and the type system. So the scope system and its functions, closures, as well as the power of the model design pattern. So this is the first of the 3 pillars according to Kyle Simpson. So the scope system and its function closure, as well as the power of model design pattern. So JavaScript is typically classify the scope system and its function closure, as well as the power of model design pattern. And I hit the brake a little here because there is a lot deep, okay. There is deep stuff that's going on here that might be quite abstract, but the reality is that they are tangible. So the scope system and its function closures, as well as the power of the model design pattern. So, couple things here: the scope system here, and what it unlocks uh, for us as the JavaScript developers. So the scope system and the closure and the power of model design patterns. So JavaScript is typically classified as an interpreted scripting language. So it is assumed by most that JavaScript programs are processed in a single top-down pass. But JavaScript is in fact parsed and compiled in a separate phase before execution begins. Exactly. You can take a look at the spec to do that, but that's what JavaScript is doing. It's now parsing. It has a parse phase, or this static semantic. It has a parse phase. It's a phase that evaluates for errors, sometimes it's syntax errors, but it has this separate phase before execution happens. And the co-author decision, but again, there are some other stuff that I ignore that I would like to dive deep into later on. So the co-author decision on where to place variables, functions, and block with respect of each other are analyzed accordingly to this rule of scope. So the variables, or the place where we define our variables, the functions, and the blocks with respect of each others, they are analyzed according to these rules before the execution happens, during the initial parsing and compiling phase. The resulting scope structure is generally unaffected by runtime conditions. Yeah, it makes sense. It makes sense. You cannot alter is the execution of this the definition of this function. Yeah, you can alter the definition, or you can alter the definition of the functions or the block or the you can extend that, you can modify that, you can modify is a definition of the parse, you can modify is a definition of how do you call you can modify is a definition of a parsing. Yeah, you can modify the definition of a parsing. You can modify the definition of a variables, functions, or blocks at runtime. so yeah, the resulting scope structure is generally unaffected by runtime condition. So JavaScript functions are themselves first-class values. Exactly, JavaScript functions are themselves first-class values. In other words, they are values. They can be assigned and passed around just like numbers or a string, but since their functions hold and access variables, they maintain the original scope no matter where in the program the functions are eventually executed, and it is called closures. So because now functions are first-class values, which is a fancy way to say that functions are values, so you can now assign and pass that pretty much like string or numbers, and because it contains now variables, all right, since functions have access or hold and access to variables, it also maintains the scope no matter which part of the code is executed. Okay, so this is called now closure. Models are co-organization pattern characterized by public methods that have privileged access via closures. So model is a way to organize these patterns It's a co-organization pattern characterized by public methods that have privileged access via closures to hidden variables and function in the internal scope of the model. Compile versus interpreting. You may have heard of code compilation before, but perhaps it seems like a mystery black box where source code sliding one end at the executable program pop up the other. It's not a mystery. It's not a mysterious or magical, though. Code compilation is a set of steps that process the text of your code and turns into a list of instructions the computer can understand. So code compilation is a set of steps that process the text of your code and turns into a list of instructions that the computer can understand. Typically, the whole source code is transformed at once, and those resulting instructions are saved as output, usually in a file that can be later be executed. This is on a typically compiled language, which is now passed through a series of a step-by-step process to transform your code into this text from your code into instructions that your computer can understand. So you also may have heard that the code can be interpreted. So how is that different from being compiled? Interpretation performs a similar task to compilation in that it transforms your programs into machine understandable instructions, but the processing model is different. So talking about is a processing model. Similar, you can think of this, all right, as a recipe. So you're preparing some meal, all right, and a compile is when you already have all the instructions and you need to only follow them to make your arepa, for example, right? You want to make a mate, arepa with mate, why not? Arepa with mate and salmon, right? Why not? So you get this, no? So this is the compile phase, or the compilation here. And the other is now the interpretation, which is the processing model here is now you're going to receive is one line of code, and that line of code will be converted into into machine code instruction, into instruction that the computer can understand, and then wait for the another one, and then wait for another one, and then wait for another one, so on and so forth. So unlike a program being compiled all at once, with interpretation, the source code is transformed line by line. Each line of or statement is executed before immediately proceeding to process the next line of the source code. Exactly. So this is compilation, and this is now interpretation, right? It has to generate this abstract syntax tree that is going to now generate is an output, usually a file, a binary file that will sit on disk, ready to be executed by the OS at that distribution. Okay, and then it enter now into the phase of the execution. So when the program now, so when you execute that program, you do double click and you hit enter in that program, and now the OS is going to load that process, it's going to load that binary file into the main memory, and then it's going to pass now so it's going to mount the, so that binary file is going to be mounted into the main memory, and then the OS create now a process that is going to pass now all of these instructions to the processor, okay, effectively creating a process. So a process, most commonly process are, for example, is the um, um, so most common process or most common example of process are the stack register, the uh, the stack, the mm, the stack, the line of code. Oh, I'll be right back. All right, and we're back. Good. Now, um, so yeah, interpretation performs a similar task to compilation, in that it transforms your program into machine readable code or into a machine understandable instruction, but the processing model is different. So, like a program being compiled all at once with interpretations, the source code is transformed line by line. Each line of or a statement is executed before immediately proceeding to processing the next line of the source code. So compile versus interpreted code. And then the figure 1 illustrates compilation versus interpretation of programs. Are these two processing models mutually exclusive? No, they are. Generally, yes. However, the issue is more nuanced because interpretation can actually take other forms than just operating line by line on source code text. Modern JavaScript engines actually employ numerous variations of both compilations and interpretations in the handling of JavaScript programs. Recall that we're serving this topic in chapter 1 to get started book. Our conclusion there is that JavaScript is most accurately portrayed as a compiled language. For the benefit of the reader here, the following section will revisit and expand on that assertion. Compiling code. Ah, there you got it. But first, why does it even matter whether JavaScript is compiled or not? Scope is primarily determined during compilation. So understanding how compilation and execution relate is key in mastering a scope. So understanding how compilation and execution relate is key in mastering a scope. In classic compiler theory, a program is processed by a compiler in three basic stages. You have the tokenization, which is breaking up a string of characters into meaningful to the language chunks called tokens. So anytime that you look at tokenization or lexing, which is something that happens a lot with these LLMs, this tokenization phase, is that breaking up that character or that data, that input into something meaningful for the language, for the large language models, called token. For instance, consider the program var a equal to. This program will likely be broken up into the following token: the var, the a, the equality, and 2, followed by the semicolon. White space may or not be persistent as a token, depending on whether it is meaningful or not. The difference between tokenization and lexing is subtle in academic, but it centers on whether or not these tokens are identified in stateless or stateful way. Put it simple, it's tokenizers. If the tokenizer were not involved stateful parsing rules, if the tokenizer were to invoke stateful parsing rules, stateful. Yeah, but it's like stateful. Okay. Mm, mm, Cortafuego. The using is too much. Okay. That's interesting. Exactly, but it's about state. It's about state. Stateful. Exactly, it's related to state. To put it simple, if the tokenizer were to invoke stateful parsing that contains a state, stateful parsing rules to figuring out whether A should be considered a distinct token or just part of another token. That will be lexing. So lexing is something that is taken in consideration. Okay, is something that should be considered as a distinct token or just a part of another token. That will be lexing. And then you have now parsing, taking a stream array of tokens and turning into a tree or nested element. Exactly, taking a string, an array of tokens, and turning into a tree of nested elements, which collectively represents the grammatical structure of the program. This is called an abstract syntax tree, which is something that I'm quite more familiar with. Okay? So the parsing is taking these strings or array of tokens and turning into a tree nested elements, which collectively represents the grammatical structure of the program. It represents the relationship, the grammatical relationship of this structure of the program. So for example, the tree for var might start with the top level node called variable declaration with a child node called identifier. Variable declaration with a child node called identifier whose value is a, and another child called assignment expression with itself has a child called numerical literal whose value is 2. Code generation, taking an abstract syntax tree and turning into an executable code. And taking that abstract syntax tree and turning into executable code. This part varies greatly depending on the language. So the platform is targeting and other factors. Okay, this part vary greatly depending on the language. The platform is targeting and other factors. So the JavaScript, exactly, this especially in the code generation. So code generation is that it takes now an input and the output is usually executable code. That is per platform, per code, among other factors. The JavaScript engine takes that just described the AST for var and turns into a set of machine instructions to actually create a variable called a, including reserving memory and etc. And then store a value into a. Note, the implementation detail of a JavaScript engines utilizing system memory reserve, etc. is much deeper than we will dig here, and we'll keep our focus on the observable behavior of our program and let the JavaScript engine manage those deeper system level abstractions. The JavaScript engines is vastly more complex than just this 3 stage. In the process of parsing and code generation, there are steps to optimizing the perform exactly. In the process of parsing and code generation, there are steps to optimize the performance of the execution. It is collapsing redundant elements. In fact, code can be recompiled and re-optimize during the progression of execution. So during this parsing and code generation, uh, the code can be even compiled again and re-optimize and doing some optimizations here and doing some optimization in the execution. So I'm painting only with broad stroke here, but you will see surely why this detail we do cover, even at a high level, all relevant. And JavaScript engines don't have the luxury of abundance of the time to perform their work and optimization. JavaScript engine don't have the luxury of abundance of time to perform their work and optimization, because JavaScript compilation doesn't happen in a build step ahead of time as with other language. It usually must happen in mere microseconds or less right before the code is executed. To ensure the fastest performance under this constraint, JavaScript engine use all kind of trick. So in order to, unlike any other programming compiler language, that they can take their time to compile that at build time, all right, and then execute it. JavaScript does also, the JavaScript engine doesn't have the luxury of the time, and it needs to go to all of these kind of tricks to do so, like just-in-time compilation, which lazy compiles and even hot recompiles. These are well beyond the scope of our discussion here, but make understand that the JavaScript itself, the JavaScript engine in itself is a wonderful machine that allows to now execute JavaScript code that allow us to transform the text of your program into tokens, known as the tokenization, or it can be lexical. Okay, the tokenization and lexing, which is something that I don't get it, lexing, that's fine, but it's a tokenization and lexing, which now create this series of tokens, and then it now builds an abstract syntax tree, or AST, based on this chunk, or based on these streams of tokens. Based on these streams of tokens, that represent now is the grammatical structure of the code, and then the code, the grammatical structure of the code, and then the code, and then that AST, it turns into an executable code, which is going to depend on the platform, the language, and other details. But in the case of JavaScript, since this is not a compiled language, if this is it, because this doesn't have a build step like compile language does, all right, to do all of this that I mentioned, it has to do that in microseconds. So the evaluation of this code, it has to do that in microseconds. So to ensure the faster performing under this constraint, JavaScript use all kind of tricks, like GST, which lazy compiles and even hot recompiles. These are well beyond the scope of our discussion here, and require two-phase. To state it simple as possible, the most important observation we can make about processing JavaScript programs is that occur in at least two phases: the parsing and compilation first, and then the execution. The separation of parsing compilation phase from a subsequent execution phase is observable fact, not theory or opinion. While the JavaScript specification does not require compilation explicitly, it requires behavior that is essentially only practical with a compile then executed approach. So for example, evaluating syntax errors. There are 3 program characteristics you can observe to prove this to yourself: syntax errors, early errors, and hosting. I am quite familiar with syntax error, and also is the early errors. Syntax errors from the start. Consider these programs. Var greeting hello, you want to print hello, and then you want to assign that to this. It's a syntax errors, an unexpected token, right? These programs produce no output hello. Exactly, this program produce no output hello if not printed, but instead throw a syntax error about the unexpected token here, right before the high string. Since the syntax error happens after a well-formed console log, if JavaScript execute top-down line by line, one will expect the hello message will be printed out before the syntax error being thrown, and that doesn't happen. In fact, the only way that the JavaScript engine could know about the syntax error on the 3rd line before executing the first of the 2nd line, okay, is because there is a difference between, it makes a lot of sense. It's because there is a difference, since this difference exists between what the spec says and what the reality is. So this exploration this is the exploration of this particular field, because unless you dive deep into the implementation of a JavaScript engine, all right, the spec might say something, but those who put that at practice and implement that, they face the reality, and therefore, well, they have to do certain stuff, okay, that tries to align with what the spec says. But the reality is, they try to do the best effort. They try to do their best effort to do that. Okay. So in fact, the only way the JavaScript engine could only about the syntax error on the 3rd line before executing the 1st line and 2nd line is by the JavaScript engine first parsing the entire program before any of it is executed. And early errors. This early error happens, for example, when you look at the spec, and you can actually determine that. So for example is the functions definitions, right? Exactly, the functions definition with use strict, for example. Next, consider the following. There you got it. Console log howdy, say something hello, syntax error, duplicate parameter, not allowed in this context, and function say something, say hey, greetings, and use a string. The howdy message is not printed, despite being a well-formed statement. Instead, just like the snippet in the previous sections, the syntax error here is thrown before the program is executed, and in this case, it is because a strict mode opt in for only the say something function here, forbids, among many other things, functions to have duplicate parameters named. This has always been allowed in non-strict mode. Exactly. And you can take a look at that from the functions definition, from the ECMAScript, that actually say that, hey, this is the early errors, static semantics early errors. But how does the engines know that the greeting parameter has been duplicated? That's a good question. You know, that's a very good question. How do you know that this is a duplicated? Okay. How does it know that say something function is even in a strict mode? While processing the parameter list, the use strict parameter appears only later in the function body. Couple stuff here. Couple stuff here. Couple stuff here. Couple stuff here. So if I hit here, it's a duplicate names not allowed in this context. Exactly. So a couple stuff here. The first statement is a well-formed statement, a console log. The second now is a function call with these two parameters, okay? And the thing here is that because we have now this declaration that happened after this function call, and also that it's going to handle this duplication of the parameter name, right? How does it going to handle that, right? And the other is that how it's going to handle that this function's definition is below of say something when the function is called previously, and it say, hey, syntax error, duplicate parameter name not allowed in this context. It say name not allowed. Duplicate parameter name, duplicate parameter name not allowed in this context. Again, the only reasonable explanation is that the code must first be fully parsed before any execution occurs. And finally, hosting. Finally, consider this code. You have now the function declaration at the top. You define your variable greeting. You now, inside of a block, you define now a block here. Okay. You define now a block here that say, hey, greeting howdy. You now define another variable here like greeting hi, and console log greeting here. And it say, hey, you define now a variable called greeting, but you can't redefine this. Say something, say reference errors. Cannot access greeting before initialization. So it is assuming is this greeting. The noted reference error occur from the line with the statement greeting howdy. What's happening is that greeting variable for that statement belongs to the declaration of the next line. For example, here, rather than the previous var greeting hello statement. The only way that the Javascript engine could know a line where the error is thrown is that the next statement will declare a block scope variables on the same name. If this is if the JavaScript engine has already processed this code in an early pass and already set up all the scopes and their variables associations. This processing of a scope and declarations can only accurately be accomplished by parsing the program before execution. And the reference error here technically comes from greeting howdy here, because once you enter into this block scope, or you can also ask a question, how is this now throwing an error? Say cannot access greeting before initialization. Reference errors, initialization. So how now is the greeting, exactly. So how now is you can redeclare these variables, and then you can reassign these variables and then redeclare these variables here right below. Okay, so something's going on here, especially with this in this segment, right? Mm-hmm. So the only way that JavaScript engine could know at the line is where the error is thrown is that the next statement will declare a block scope variable on the same name greeting. If it is the JavaScript engine has already processed this code in an early pass, all already set up all the scope and their variable association. This processing of a scope and declarations can only accurately be accomplished by parsing the program before execution. So the reference error here technically comes from the greeting howdy accessing the greeting variable too early, a conflict reference as the temporal dead zone. Chapter 5 will cover this in more detail. Warning, it is often asserted that let and cons declarations are not hosted as an explanation of the TDC behavior just illustrated, but this is not accurate. We'll come back and explain both of the hosting and TLC on let and cons in chapter 5. They are hosted, but they are hosted, but the assignment. Mm, Hopefully, you are now convinced that JavaScript programs are parsed before any execution begins. But does it provide they are compiled? This is an interesting question to pound, but exactly. But does it prove they are compiled? This is an interesting question to ponder. Could JavaScript parse a program, but the execution that program by interpreting operations represent in the AST without first compiling the program? Could JavaScript parse a program, but the execution, but then execute the program by interpreting operations representing in the abstract syntax tree without first compiling the program? Yes, that is possible, but it's extremely unlikely, mostly because it will be extremely inefficient performance-wise. It is hard to imagine a production quality JavaScript engine going all the trouble of parsing a program into AST but not then converting, aka compiling the AST into the most efficient binary representation for the engine to then execute. Many have endeavored to split hairs with this terminology, and there is a plenty of nuance and actually interjections floating around. But in spirit and in practice, what the engine is doing is processing JavaScript programs in much more alike compilation than not. In much more alike compilation than not. Classifying JavaScript as a compiled language is not concerned with the distribution model for its binary executable representations. Because it's interesting, compiled language are the definition is based on its distribution model, but for it is binary executable representation, but rather in keeping a clear distinction in our minds about the phase where JavaScript code is processed and analyzed. Is keeping a clear distinction in our mind about the phase where JavaScript code is processed and analyzed. This phase, observably and indisputable, happens before the code starts to be executed. So we need a proper mental model of how the JavaScript engine treats our code if we want to understand the JavaScript and the scope effectively. Compilers speak with awareness of the two-phase processing of JavaScript programs, compile, then execute. Let's turn our attention on how the JavaScript engine identifies variables and okay. So now that we know that this two-phase processing of JavaScript programs happens, or yeah, happens, let's turn our attention of how JavaScript engine identify variables and determine the scope of a program as it is compiled. First, let's examine the simple JavaScript program to use for analysis over the next several chapters. Okay. You have now an array that is assigned. You have now an array that is that have a series of objects as values. All right. That is now assigned to a student var. We also have now a functions get student name, which is another way of how you can define a variable in JavaScript. Okay, you pass now the student ID. You define here some iteration using now is the for of loop, okay, as a way to now iterate through this elements, and then you going to check that if it is, now return me is the student name, otherwise return nothing. So for next student is another variable here when you are now assigning is the output of this get student, which can be is undefined, or in this case is now 73, which is the ID of that. Let me copy here, which can be Susie, right? But if you for some reason pass something that is not, it's gonna return now undefined. So other than declarations, all occurrence of variables identifiers in a program serve in one of these two roles. Either they are the target of an assignment or they are the source of a value. Other than declarations, exactly, other than declarations, all occurrence of variables and identifiers in a program and identifiers, all the occurrence in variables and identifiers in our programs serve in one of the two roles. Okay, all occurrence of variables or identifiers in our programs serve in one of the two roles. Either they are the target or of an assignment. So if this is the target of an assignment, yes, yes, and yes, or either is a source of a value. In this case is this. When I first learned compiler theory while earning my computer science degree, we were taught that the term LHS, aka target, or left hand side, and the right hand sides, aka source, for this role respectively. As you might guess, the L and right are the acronym from left hand sides and right hand sides, as in left and right sides of an equality assignment operator. However, assignment targets and source don't always likely appear on the left on the right. Assignment targets and source don't always literally appear on the left or the right end. So it's probably clearer to think in terms of the target and the source rather than the left and the right. Okay, so we are getting to the weeds of the mathematical definitions of this assignment. So how do you know if a variable is a target? That's a good question. A variable is a target of a variable is a target of a variable is a target of the assignment A variable is a target of an assignment. A target is a variable of an assignment. A variable is a target of an assignment if they're assigned a value to. Check if there is a value that is being assigned to. Exactly. If there is a value that is assigned to. So if so, it is a target. If not, then the variable is a source. So for JavaScript engines to properly handle a program's variable, it must first label each occurrence of a variable as a target or source. For each occurrence of a variable, the language must label that as a target or as a source. And we'll dig into now to how each role is determined. So what makes a variable target is if you assign now a valid expression. This statement is clearly an assignment operation. Remember, the var student part is handled entirely and a declaration at compile time, and this is irrelevant during execution. So we left it out for clarity and focus. Same with the next student get student statement. So it's now a target of an assignment. But it's all about is this is determining is the occurrence of variables and identifiers. They're either a target or the source of an assignment. They're talking about is assignment. Okay. So the talking is about is assignment here. Of assignment here. Okay. If this is the assignment here. If this is the assignment here. If this is the assignment here. This statement is clearly an assignment operations. Remember the var student bar is handling entirely as declaration at compile time. And is thus irrelevant during execution. This okay. Where it left out for clarity and focus. Same with the next student, which is now an statement of assignment. But there are 3 other target assignments operations in the code that perhaps are less obvious. One of them is this. Okay, but there are 3 other target assignments. The statement assigns a value to a student via the iterator here. For each iteration on the loop, another target reference. And here is this. But how is that an assignment to a target? So look closely. The argument 73 assign is the parameter to student ID. And there is one last subtle target reference in our programs. Can you spot it? Yes. Did you identify this one? Yes. A functions declaration is a special case of a target reference. You can think of it sort of like var get student name function student ID, but that's not exactly accurate. An identifier get student name is declared at compile time. An identifier get student is declared at compile time, but the value, the assignment function student ID part is also handled at compilation. The association between get student name and the function is automatically set up the beginning of the scope rather than waiting for an assignment statement to be executed. The automatic association of a function and variable is referred to as function hoisting and is covered in detail in chapter 5. Source. we have identified all 5 targets in the programs. All 5 targets, all targets, uh, all targets of an assignment. Target of an assignment here. But how this is an assignment to a target? Because we are assigned is the value of the argument 73 to a parameter student ID. And we're assigning is now the value of that student on each iteration and similar to the student. So there are now target here. Assignments to that. Holy shit. Okay. The automatic association of a function and variable is referred to as function hosting. And the other is source. So we have identified all 5 targets referenced in the program. The other variable's reference must be the source reference. So anything that is not a target of an assignment is now a source, because that's the only other option. So for okay, is the source of an assignment, is the source of an assignment and the target of an assignment. What do you mean by target and source of an assignment? But that is okay. That is when that happened. If this is the target of an assignment, or if this is the source of an assignment. So for let student, so we're how you can describe this, because when that assignment happens, if this identifier or variables, holy hell, if this identifier or variable here is this identifier or variable here, holy moly, is this identifier or variable if this identifier or variable, the assignment, if it is a target of an assignment or the source of an assignment, and the target is when is this assigned here. Okay, so if this is the target of an assignment, so the value is now assigned to that. In this case, yes. So we say that student is a target, but student, how do you define it? Is this the target? No, because you're not assigning to. So this is the source of the assignment. Is a source reference. In the statement, if student.id is equal to student.id, okay, what is a source and what is a target? Well, no, you are not a sort of an assignment or this, but both of them are the source. Exactly. So both of them are the source reference. Student is also a source reference in return student.name. Okay, student is also the source reference in return student.name. In get student name 73, because you are assigning that parameter, that argument with that, you're assigning is this argument with this parameter. Get source is the source reference. Okay, so you are not assigning anything to a variable or to an identifier, which we hope resolve to a function reference value in console.log next student. Console is now the source as is next student. In case you were wondering, ID name and log are all properties, no variable reference. What's the practical importance of understanding target versus source? Yeah, that might be quite interesting. In chapter 2, we'll revisit this topic and cover how a variable role impacts its lookup, especially if the lookup fails. In cheating, runtime scope modifications. It should be very clear by now that the scope is determined as the program is compiled and should be now generally be affected by runtime conditions. However, in non-strict mode, there are technically still two ways to cheat this rule. Modifying a program scopes during runtime. Modifying a program scope during runtime. Neither of these techniques should be used. They are both dangerous and confusing and should be used as strict mode whether they are disallowed anyway. But it's important to be aware of them in case you run across them in some programs. The eval function receives a string of code to compile and execute on the fly during a program runtime. If that string of code has a var or functions declaration in it, those declarations will modify the current scope that the eval is currently executing. If that string or code has a var or function declaration in it, those declarations will modify the current scope that the eval is currently executing. So in other words, okay, with eval you can even define as functions. So it's gonna define, you can, okay, holy hell. If this is to runtime scope modification. So if the eval has not been present, the oops variable in the console.log oops will not exist and will throw a reference error. But the eval modify the scope of a bad idea function at runtime. This is a bad for many reasons, including the performance hits of modifying the already compiled and optimized scope every time bad idea runs. The second cheat is the with keywords, which essentially dynamically turns an object into a local scope. Its properties are treated as identifier in that new scope block. Holy hell, so you're turning that into, oh, that I don't. The global scope was not modified here, but bad idea was turned into a scope at runtime rather than a compile time, and its property oops becomes a variable in that scope. Again, this is a terrible idea for performance and readability reasons. At all costs, avoid eval, at least avoid creating declarations, and with. Again, neither of this cheat is available in strict mode. So if you use strict mode, you should, then the temptations goes away. In the lexical scope, we have demonstrated that JavaScript scope is determined at compile time. Determined is exactly the JavaScript scope is determined at compile time. The term for this kind of scope is lexical scope. Lexical is associated with the lexing stage of compilation, as discussed early in this chapter. The lexing, the stateful. The lexing. If the tokenizer would invoke stateful parsing rules to figuring out whether A should be considered a distinct token or just part of another token, that will be lexing. And here it should be very clear by now that the scope is determined. Nope, it's here. Lexical is associated with the lexing state of compilation, as discussed early in this chapter. To narrow this chapter down to useful conclusion, the key idea of lexical scope is that it's controlled entirely by placement of functions, block, and variables declaration in relation to another. If you place a variable declaration inside a function, the compiler handles this declaration as it is parsing the function, and associate that declaration with the function scope. Exactly. So if you place a variable inside of a function, the compiler handles these declarations and it is parsing the function and associate that declaration with the function scope. If a variable is block scope, declare let. If a variable is block scope, declare let and const, then it is association with the native enclosing block, rather than an enclosing function as with var. Furthermore, a reference, target, or source role for a variable must be resolved as coming from one of the scope that are lexically available to it. Yeah, a reference, target, or source for a variable must be resolved as coming from one of the scope that are lexically available to it. Otherwise, the variable is said to be undeclared, which usually result in an error. If the variable is not declared in the current scope, the next outer enclosing scope will be consulted. This process of stepping out one level of a scope nesting continues until either a matching variable declaration can be found, or the global scope is reached and there is nowhere else to go. It is important to note that the compilation doesn't actually do anything in terms of reserving memory for scope and variables. None of the program has been executed yet. Instead, compilation creates a map of all lexical scope that lays out what the program will need while it executes. You can think of this as an insert code for use at runtime, which defines all the scope, but again, it's a map. The compilation creates a maps of all the lexical scope, functions, block, and global, that lay out what the program will need while it executes. And you can think of this plan as insert code for use at runtime, which defines all the scope, aka lexical environments, and register all the identifiers variable for each scope. In other words, while scopes are identified during compilation, they are not actually created until runtime. Each time a scope needs to run, in the next chapter, we'll sketch out the conceptual fundamental for lexical scope. So that was mind blowing. But the thing here is that we're talking about source and the target here, but based on the reference, variables reference. So for example here, furthermore, a reference, target, or source role for a variable must be resolved as coming from one of these scope. So when you want to resolve if the variable reference, whether it's the source of an assignment or the target of an assignment, okay, they are resolved. So they are resolved as coming from one of the scope that are lexically available to it. Otherwise, the variable is said to be undeclared. And if the variable is not declared in the current scope, it will next outer the enclosing scope will be consulted until there is no exactly. And this process of stepping out one level of the scope, nesting continues until either a matching variable declaration can be found, or the global scope is reached and there is nowhere else to go. It's important to know that that compilation doesn't actually do anything in terms of reserving memory for a scope. It's more like a map. It's more like a map of all the lexical scope. But again, the idea of talking about the target and the source is mainly because how these assignments happen. Okay, hey, this assignment for these variables referring is the source. Is the source or is the target? And it has now a map uh, of all the lexical scope here. Illustrating lexical scope here. Mm-hmm. And the scope change. Mm-hmm. Where exactly is the global scope? Browser window. And web workers. Developer tools console log rel. Mm-hmm. Then EX6 models. And globally aware. In chapter 5, the not so secret lifecycle variables. Mm-hmm. Declaration versus expression. Mm-hmm. Mm-hmm. In chapter 6, least exposure. Mm-hmm. Scoping with blocks. Mm-hmm. And then you have now a couple appendix here. Imply parameter scope. Function name scope. Anonymous versus name functions. Explicit or inferent names. Names as descriptors. Mm-hmm. Closure part 2. And the suggestion solution. And models. by exposing is that okay, so that'll be all for this video. Take care. Bye bye.